Both natural numbers and real numbers are infinite, but their infinities are not the same. While natural numbers are countable, real numbers are uncountable. Mathematics proved this fact more than 100 years ago, with nothing more than a single diagonal line. So how can one diagonal prove that real numbers are uncountable? The proof by contradiction is applied. We assume the opposite. Real numbers are countable. And from that assumption, we are going to reach a contradiction. But when does the diagonal come into play? It enters at the most crucial moment, exactly when the contradiction appears. Now, let's begin the proof. Although we are talking about all real numbers, we'll only use real numbers between 0 and 1. There are infinitely many numbers here too, and the size of this infinity is mathematically the same as that of all real numbers. What does it mean to say real numbers are countable? It means that, like natural numbers, we could list them one by one, pairing each real number with a unique natural number, not necessarily in size order, just any complete sequence that includes every real number. This is the list of natural numbers. That is the complete list of real numbers. There would be no real number outside this list. Each real number is represented in decimal form. A1 for the first, A2 for the second, and AN for the nth. Now, what should we do next? Exactly, we need to find a contradiction. That contradiction will appear if we can show that some real number is missing from this list. So let's create this missing real number n. To find its digits, we draw a diagonal across our list. The first digit of A1, the second digit of A2, the third of A3, and so on. Take each diagonal digit and, if the digit is not 1, replace it with 1. If it is 1, replace it with 2. That's the nth digit of the number n. Continue this rule. You've built a new real number n. Now, let's compare n to every number in this list. N is not equal to A1 because at least its first digit is different. It's not equal to A2. At least its second digit is different, and so on. N is different from every AN at least in one digit. But n is clearly a real number between 0 and 1. And yet, it's not in our complete list. That's a contradiction. If every real number were listed, n should have been there, but it isn't. So, our assumption, real numbers are countable, must be wrong. Real numbers are uncountable. No matter how many you list, there will always be another real number that is not included in the list. The diagonal reveals exactly that, and that process itself is infinite. The rule that generates n can continue forever. By applying the rule, if the digit is not 2, replace it with 2. If it is 2, replace it with 3. The number n generated by this rule is also different from every an. In this way, we can see that real numbers that are not included in the list are actually infinite. This brilliant idea was first proposed by the mathematician Cantor in 1891. That's why it's known as Cantor's diagonal argument. With one diagonal, he changed the way we understand infinity. Later, the diagonal method became the key to major breakthroughs, from proving that every power set has a higher cardinality than its original set, to inspiring Turing's idea of the halting problem in computer science. The diagonal has always been a tool to build something that lies beyond any complete system. Did you enjoy this math traveling? Subscribe for the next. Thank you.